Okay, I'm going to begin this video by pulling up a screen that is again going to look like a whole bunch of jibber jabber. Right here. Okay, referred to as limit laws. So this will be posted on the page. And again, you probably look at that and think it looks like a foreign language. One of the things that it's showing you, if you look at the example down below, and no one does limits this way, right? This is just verifying that we're allowed to just plug in. If we want to find the limit of this rational function as x approaches 2, we can just plug in. That's the quotient law because there's a quotient, right? Then you can move the constants in front and find the limit of each term separately and add them together. So that's really just telling you in very complicated terms to just plug in for x, okay? But here is something that's going to be important to us, okay? What this does tell us is that the limit of the, all right, and then I'm going to add in here in text, the limit of whether it's the sum, I'm going to write it like this, because I could write each one of these three things all separately, but I'm going to write them all like in one spot. I guess I don't need that line. Can I delete that? I can. Okay. So the limit of the sum, difference, product, or quotient is the sum, product, difference, and quotient. So I could have written this 4 times. Okay, the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of the product is the product of the limits. And the limit of the quotient is the quotient of the limits. Okay, so I wrote this only once, and so it would read like this, right? The sums would go together. The difference, oh, that should say difference, not different, but I'm not going to change it. The product and the quotient. Now there is a little bit of fine print that goes with this theorem. The fine print of this theorem says, as long as both limits exist and you don't, for the quotient, you don't divide by 0. Okay, so that one is specific to the quotient. All right, so the limit of a quotient is the quotient of the limits as long as they both exist, both limits exist, and I'm not trying to divide by 0. All right, so moving on, let me show you something that's going to look kind of strange, right? That when we are working with a limit, right, and you're given a limit problem, it always looks like this. It's always the limit, and here's the function as x approaches something, right? So the function might be x squared. If this were x squared, you'd say the answer is 4, right? But what about this? The limit of 5 as x approaches 2. Like, I don't have a function there. I just have a number, right? But 5 actually is a function. That is the function y equals 5. And if I draw it, right, I labeled y equals 5 right here. If I draw it, it is a horizontal line at y equals 5. Okay, so that is in fact a function known as, of course, a constant function, which means if I go here on my x-axis and go to 2 and say, well, if I stand close to 2, what functional values do I see? I see functional values that are 5, right? It's a constant function. No matter where I stand, I see functional values not even close to 5. They're just always 5. Okay, so that might look kind of weird that if you are given a limit, no matter what you're approaching of some constant, the answer is just, the constant value. Actually, I meant to write, well, this would be -10. I actually meant to write limit of 5 as x approaches negative 10. That's actually what I meant to write there, because that's what's illustrated up above. Okay, that this answer is always 5 no matter what. So I miswrote it, but that's fine. Then there's just a different example with a different constant in there. So the next thing that I want to do is introduce you to the skeptical mathematician. Okay, mathematicians like things proven. And I don't think your high school teacher, your pre-calc teacher probably didn't do a ton of stuff with proofs for you. But in this example, right now, if I plugged in, I'd get sine of 0, which is 0. So I'd get 0 over 0, right? And I'd turn to my calculator. And I'd say to the skeptical mathematician, I'd be 1/10 away from 0. And I'd say, look here, 0.9983. Don't you think that's close to 1? And look, it's the same from both sides. And they'd say to me, nah, I don't think so. I don't believe you that the limit is 1. Right? So then I'd go to 1/100th. And I'd say, well, look, now I'm even closer to 1. And they'd still say, nah, I just don't believe you. Right? It could stop with 29s. Right? And how do you know that doesn't happen? Right? Or how do you know if I got closer and closer and closer that something didn't change? Like all of a sudden I start seeing functional values close to 2. How do you really know that? And again, I don't really know that because my table on my calculator, it's evidence that the limit is 1, but I can't get any closer than this using table on my calculator. So I really, I want to call this 1, but a skeptical mathematician would look at that and say, nah, I don't know if I believe you. You're not close enough to 1 for me. Okay, so what I can do in this case is I can use something. I can actually prove that this limit is 1. And one of the things we're going to do next week when we're back together in class is I'm going to talk about how to satisfy this skeptical mathematician. But one of the things that we can do here is use what's known as the squeeze theorem or pinching theorem. So what that does is it says if the function in question gets squeezed in between 2 other functions, then I know all 3 of these right at this point would have to have the same limit. And that can happen with this sine of x over x. Okay, here's the line y equals 1, which what we just saw a minute ago, and it looks kind of weird, but what's the limit as x approaches 0 of 1? It's 1, right? And then if I come over here, well, if I plug in 0 for cosine of 0 is 1. Okay, so the function in question is this green function. It got pinched in between 2 other functions for whom I know that the limit is in fact 1 when x approaches 0. Therefore, this is proof that this is actually 1. Since I've proven this, I can use this fact in other problems, okay? Which again, next week when we're back together, we're going to do that. So for the moment, this is just a little foreshadowing of a few things to come. So we're gonna use this fact next week, and we're also going to talk more about the skeptical mathematician and how we're going to satisfy that person when they don't want to believe us when they see evidence. All right, those tables of values are evidence. It's not proof that that is the limit. Let me just show you what the homework looks like for this section. Okay, so using these limit laws, the limit laws tell you that if you have a constant, that you can move the constant out in front. Okay, and then here I have a product. So I know that the limit of a product is the product of the limit. So I can just multiply this limit by this limit. All right, and I should have an x approaches 6 below each of these, and I'm going to get lazy and not write it. And then I just look up above and say, well, the limit of f of x as x approaches 6 is 4, right? So it's 2 times 4 and the limit as x approaches 6 of g of x is 9. So let's see, that's 8 times 9, which is 72. Okay, so that's how these exercises work. So the limit of a product is the product of the limits. You know, come down here and like this one, right? What's the limit of x as x approaches 6? That would just be 6. And then that would be multiplied by the limit of h of x as x approaches 6, which let's see, what's h of x? That would be 6. All right, so 6 times 6, right, is 36. Okay, so all you're doing is applying, you know, like right here, the limit of the sum is the sum of the limits, right? So in place of the f of x, the limit as x approaches 6 for f of x, that would be 4 plus, and then you've got a constant multiple, so you just put that in front, and then you put the limit of g of x as x approaches 6, which is 9, and then you compute. Okay, so that's all the exercises involve with these laws. But sometimes these laws help us prove things. Like they actually do have some places where they're useful, where we have one law, we use it to prove another law, and then we get this other law and it helps us prove something else. And that's kind of the chain reaction that happens in mathematics. So again, thanks for watching, and we'll pick up with some of this next week.